Alright, so yesterday I gave you that introductory handout. I introduced you to the world of work, you could say. Some new units, some new ideas kind of thing, but it's really pretty straightforward. Let's have a quick look here before I do these actual sample questions. The first sheet that I handed to you, calculating work done in various situations. And I think I may even have a copy of this. I'll just wing it. Okay, so work done in various situations. Case number one, a force acts on a mass and accelerates along a frictionless surface, or, so this one here, the one that says calculating work done in various situations. Or if friction is present, the object might just move along at a constant velocity. In either case, energy is transferred to the mass, work is done by the force, and it can be calculated by W equals Fd. That's the basic formula. It's the definition of work. Force multiplied by distance. But consider motion at a constant velocity across a frictionless surface. Once the object is moving, no force is required to maintain the motion. Thus, there is no work done. So if either force is zero or the distance is zero, then what does that mean about the amount of work? Also zero.
So like you're like pushing super hard on the filing cabinet, but it's not moving. No work is done.
No work. No distance. I can push as much as I want, as long as it doesn't move. No work. In the scientific work sense. Case number two, if when an object is lifted vertically, work is done against the force of gravity. Note that the force needed is the weight of the object, so mg, and so the work done is really, and I'm deriving a formula here really, F times d. The weight force is mg. Work done in this case, mgd. And there's always someone to ask. I don't think I've ever taught this without someone giggling or something, make some comment about the beer. Which then I write mgh for height instead.
Well, I can
Whatever, man. La 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 la. Case number three, object is tied down, can't move. How much work done? None. No work done. It's like Friday afternoon. No work done. I need a smile. Case number four, you got something like a big statue sitting on a pole. Any work done? On the left there? No work done. Weight force, no work done. D is zero. What about a skinny, bald-headed man carrying his briefcase awkwardly in front of him like that? No work done. How come? Is he applying a force? Yes, but what's the difference with the skinny, bald-headed man carrying the briefcase awkwardly? Well, he is, right? We've got weight force down, and we'll call it like an applied force up, but what direction is the distance? The distance, here's another rule, the distance and the force must be in the same direction. Yes, in my younger, thinner days. You can't laugh at yourself, you can't laugh. What about circular motion? Is the d distance or is the d displacement?
Distance.
Well, second of all, let's go back to uniform circular motion. Which direction is the force? Inward. Inward towards the center of the circle, but the distance or the displacement is not in the same direction. So once again, what does it say? No energy transfer, i.e., no work done. There's a lot of non-work happening here. A lot of cases where there's no work. What about if the force is exerted at an angle? Okay, now they sort of made that a little confusing down there. But if you've got an angle like this, if this is your applied force, and you've got, they label them Fx and F perpendicular. We can call them Fh and Fv. The work done in this case is actually, is it going to be the F, the FH, or the FV that's providing the force? And the answer is it's the horizontal component, right? It's got to be the force in the same direction as the displacement of the distance. Does that make sense? Yeah? Like it's like that horizontal component that pulls it sideways, right? No, Brandy? Don't like it? The horizontal component is the same direction as the actual displacement. What's the vertical component doing here? Taking away some friction, right? Making it easier, but it's only the FH that is contributing towards the work. Okay, let's jump right in and do some samples. I don't think they can get any easier than these sample questions, you guys. I really don't. I think you'll be overjoyed with the simplicity. How much work is done when sliding on a 30-kilogram chair? When sliding a 30-kilogram chair, this is 15 meters across a rough surface where the force of friction is 50 newtons. Let's draw a diagram. It doesn't say constant speed, but do you get the feeling that it should say constant speed? It doesn't say acceleration though, does it? Right? So I think we can assume that the acceleration is 0, constant speed. So we've got 30 kilograms. The distance is clearly 15. What's the force? Is it going to be the weight force, or is it going to be that 50 newtons? Okay, well, it's sliding on a surface, so I got weight force down, I've got normal force up, and I've got a friction force of minus 50. Which means my applied force must be also 50. So do I need to go 30 times 9.8? Probably 290, I think. What's my force? The force must be in the same direction as the direction. So which force do I use? Come on, be brave. It's the 50. It's 50 times 15. 500, 750. Did I do that right in my head? Do you know why it's the 50 and not the 30 times 9.8? Because it's got to be in the same direction as the distance.
Will we ever have questions where it's not just...
What about work done against gravity? How much work is done lifting 2 bricks, each a mass 1.4 kilograms, from the floor to the top of your table, which is measured to be 80 centimeters? Are warning bells going off about the 80 centimeters? 0.8 meters. There's 2 bricks. 2 times 1.4 is 2.8 kilograms. We are doing work against gravity. Weight force is mass times gravity. 2.8 times 9.8. Just so I can avoid writing down MGD, I'll leave it like this, do it 2 steps. $27.44. Work equals FW times D. .8. 21.95. 21.95 what? Do you remember from yesterday? Joules. Joules of work, capital J. Anyone find any joules of food energy on any food items last night? Just, yeah. I had Vector this morning, first time in a while. I didn't even look. It's good, it's always good. Probably too much sugar. Always is. But probably better than like, Fruit Loops. Do you want to try this one? I'll draw a diagram for you. What are your spider instincts telling you to do? You guys have these, right? Don't you? You have the questions typed out, right? Okay, good. What should I do first? Emily, what should I do first? Do you think? I don't know. It's at an angle. We got to find the force that's in the same direction as the distance, right? So what do I have to find? I got to find FH. And that's going to be FA cos theta. So 25 newtons times the cosine of 30 degrees. $21.7, right? Now just, W equals FT. 21.7 times 4. Are you feeling better about this unit now? So far so good? No? It's going to be too much work? Oh, well, we got to talk about kinetic energy, potential energy, spring energy. That'll put a real bounce in your step.